right. Well, good morning, good afternoon, everyone, and welcome to today's Exploring by the Seat of Your Pants event. My name is Joe Grabowski, and I'll be your host for today. This is the last week of November, but there's still lots going on before December kicks in. There'll be a newsletter coming out today, which is going to have some really cool features in it, including a really exciting announcement about the Artemis 2 mission going back to the moon, which launches early in the new year. We have a really exciting announcement, so keep your eyes peeled for that and get in on this special event coming up with your classrooms. Today, we are doing what we love to do, and that is to go live into the field. And we're doing it with a team who we've spent a lot of time with, at least a few times a month since the school year started. We are hanging out with the Around the Americas expedition. If you don't know already, it's a 14-month voyage. It set sail in May. Their goal is to make their way around North and South America aboard the 48-foot sailboat One Ocean. The mission focuses on scientific research, education, and community outreach. It's all about raising awareness for the health of our oceans. Now, this is building on a previous journey in 2009, 2010 by Captain Mark Schrader. And collecting these new results will allow them to look at the way that the ocean has been changing over the last 15 years. So let's reach backstage and let's bring in the team right now. It looks like they're having a great sailing day. Here's some of the team coming in. Hey, everyone. How we doing?
Hello. Good. How are you, Joe?
Good. It's great to see everybody. Last time we connected, you were in Puerto Rico, I believe, and now it looks like you're back out on the ocean.
Yep, we're back out in the ocean. We're headed towards Panama right now, but we're in the Caribbean Sea. We're going to do a little buoy drop here in just a moment.
All right. I just pulled the map up here quickly so we can see the progress has been made since our last connection. We can go back in time and see the distance covered already. Yeah, it is so much fun to be doing these connections and to follow your progress.
Yeah, and we look to our left here at port side. Venezuela and Colombia are about 200 miles that way. Panama is about 500 miles that way, and the Virgin Islands are 500 miles behind us. We didn't expect to be heading to Panama, but contrary winds and weather meant we had to rethink how we were going around South America. So we're going to go through the Panama Canal, and weather permitting, we'll turn left up to the canal and continue the circling of North and South America.
All right. Well, I think that's one thing that we all know about expeditions is you have to be flexible. Nothing goes 100% to plan. A lot of things are out of your control. So it sounds like you're making the best out of the situation that you got in front of you.
We hope so. And right now, this is what 20 knots of downwind Caribbean sailing looks like. And somebody else is steering, and that's the autopilot. So that's how we're really enjoying today, and really good to have you all here.
Excellent. Well, why don't we get a quick team introduction for those who might be new to what we're up to. And then I think you've got something pretty cool we're about to do as well.
Yeah, so right now the Around the Americas crew is joining you guys live from One Ocean. I'm Tess, and we have Jennifer Dalton, the project director, behind the camera. Mark Schrader, who's at the helm. He's our captain. And we have a new crew member, John. So he just joined us in Puerto Rico. And then also, as you can see, we have Grace Dalton, who's our lead scientist, and Mike Beamer, who's our engineer. And they're joining us virtually today. And then we also have special guest speaker Andy Jessup joining us. So we're super excited to have Andy with us. But we're going to do a quick buoy drop before we let him take over.
Right, and are we dedicating this buoy to anybody in particular?
Yes, we are. This buoy is dedicated to students in Ukraine at the Educational Institution of Jessup. And we also wanted to give a shout out to the South Carolina schools that have been joining us throughout this entire expedition. So thank you, Sailors for the Sea, for sponsoring these buoys. And we're going to go ahead.
I think so now. Have you instructed John not to jump in with the buoy?
Yeah, just the buoy, not yourself.
Just the buoy.
Okay, it's buoy number 157, and you'll be able to track that live from our website, everybody, www.oneislandoneocean. All right.
And you'll check out the wave height and where this buoy
Yeah,
goes to.
I think we've all guessed what our wave heights we're going to see today. And so Tess will post that, and you guys can put your guesses in as well.
Yeah, everybody guess how high these waves are.
Okay.
Okay, I'll wait for a big.
All right.
Go for it.
Go for that.
All right.
Alrighty. Start tracking, everyone.
5 weeks of tracking on that buoy, so watch that buoy.
Okay.
All right.
Think think of Ukraine and think about Charleston and to let people know what's going on with these buoys.
Yeah.
Okay.
Very cool.
Yeah.
Well, it's great. I think that's our third live deployment, so that's pretty cool. For anyone who might be new, what kind of data are you going to be able to grab from that buoy? I know you just talked about wave height. I'm sure temperature. What else can we grab from it?
Ambient noise
Correct.
and current. So also drift. So how far the buoy's drifting and where it's drifting.
And that's it. And so, yeah, wave height, ambient noise, temperature, and drift. So you can tell what the currents are doing here. By the way, the water temperature right here, Andy will talk about it in a little bit. 90 degrees, just a little bit over 90. It's been over 90 since, I think, Bermuda.
Since Bermuda. Yeah.
All right.
All right.
Very
Take
cool.
it away, Andy.
What do you say? Let's get Andy Jessup in here. He's been waiting very patiently backstage. I know that today we're going to talk a little bit about heat flux and water temperature with Andy. So let's get him in here live with us right now. Hey, Andy.
Hi, everybody.
Hi,
I'm
Andy.
coming
Thanks
to you
for
from
joining us.
Seattle, Washington. And it's a great opportunity to do this live. So shall I start my presentation now?
Absolutely. I'm going to fill you into the screen. You are now full screen, and I'll watch for the presentation. There we go.
Okay. Well, thank you so much for this opportunity to join you and tell you about my research. I'm a physical oceanographer. That means I study the physics of the ocean at the Applied Physics Laboratory in the University of Washington in Seattle. And I study sea surface temperature, which is important for understanding how heat and, as I'll mention, gas are transferred between the ocean and the atmosphere. So I also want to tell you about a special effect that we study when we look at sea surface temperature on the ocean, and that's called the cool skin effect. So I'll get started here with first, this is a temperature map of the ocean temperature that's measured by a satellite. Satellites are one of the most important tools now used in oceanography, and that's relatively new in that 50 years ago or so, the first satellites went up in the 1970s, and it revolutionized oceanography because we can put a satellite up in space and it can measure all types of things over the ocean, and it can do that in a few days compared to before satellites when we only had ships to go out at sea, and it would take a long time to cross an ocean and things would change over that period of time. So this map shows you the land masses, and then it shows you the temperature of the ocean. And you can see that on this temperature scale here, cold colors are cold, blue and purple are cold. 0 is freezing. We're using the centigrade scale here, where 0 is freezing. And then these temperatures up here in red, those are very warm, like 80 or 90 degrees as they're having now on the ship. So you can see it's very warm at the equator, and it gets colder as we go north and south to the poles. Well, you might wonder, how does a satellite make these measurements? Well, it doesn't have we can't put the thermometer in the water like this, but we can measure it remotely. And we do that by using infrared radiation to measure the temperature. So just like you can feel the heat coming off of a fire with your hands, we have special sensors called infrared sensors that can measure the heat from the ocean and all of the earth and give us a measure of what the temperature is. So I want to show you a video that I made a while ago that demonstrates the usefulness of these infrared cameras. My name is Andy Jessup. I'm a scientist and I study heat. What we use is a special camera here, which is an infrared camera. It's sensitive to heat radiation. Our eyes are only able to see visual light, but this special camera can see thermal radiation. It's a map of temperature. The blue is cold and the red is hot. I'd like to show you how we can see radiant heat as it heats up an object. This is an infrared heat lamp. We have a piece of black paper here, and I'm going to turn the lamp on, and as we watch the display, you can see that the pattern of heat is growing. It's getting hotter in the middle as the radiant heat is transferred from the lamp to the paper. Very cold things like liquid nitrogen at minus 200 degrees centigrade still emits thermal radiation. This now is how the imager sees something very cold. Even very cold material radiates some heat. Okay, so that gives you an idea of what we can do with these thermal infrared cameras to measure temperature remotely. Now let's think about what happens at the surface of the ocean, where the ocean and the atmosphere are exchanging heat and gas and energy. The main source of heat for the Earth, of course, is the sun. The sun hits the ocean, and that gets absorbed, and then the heat gets re-emitted because the ocean can't keep heating up, so it also loses heat after it gets heated up. We also have a process of evaporation from the ocean surface, which is very important. That's probably the largest way in which heat gets removed from the ocean, and we're going to talk a little bit about that more in a minute. And then there's heat that we call sensible heat. It's the heat that is because can be a temperature difference between the water and the air. And then when the wind blows over this, or if it rains, then it all gets mixed up, and the processes, the temperature that we see will depend on how these processes affect that. Now, if you think about the ocean, I want you to think about how the ocean loses heat. And if you think about this, it's like in terms of evaporation, it's very similar to the way that you lose heat when you get hot. So if you get hot and you start to sweat, you have little sweat glands in your skin. That sweat comes out and it wets your skin, and that sweat evaporates and it creates a cool skin on your body. And the same thing happens on the ocean. And the reason that we lose heat is evaporation is the process of changing a liquid into a gas. And that change of state takes energy, and that energy comes from heat. And so when your body loses heat, when your sweat evaporates, your body loses heat and you cool down, the same thing happens on the ocean. So if you think about a cartoon here where we have water and air, if we have evaporation and we're losing heat, then there's a thin layer near the ocean surface that's a little bit cooler than the water down below. And we call that the skin temperature because it cools off just like your skin cools off when you sweat. Then the temperature below that we call the bulk temperature. And what's important is the size of the difference between these two temperatures. If you have a very large difference, that means you're going to lose a lot of heat. If you don't have any difference, then you won't be losing any heat. So we compute what we call the bulk skin temperature difference. We call it delta T using a Greek letter here. That's the difference between this measurement that we would make of the skin and the measurement we make of the bulk. And on the ocean, that's relatively small. It's a few tenths of a degree. It can get up to half a degree under very low wind speed conditions. Now, so we want to make measurements of this. Well, we can make a measurement with the bulk temperature just by putting a thermometer in there. But with the skin layer, it's only about 1 millimeter thick. It's a very thin layer. That's about as thick as this dime coin. So we can't put a thermometer in here to measure that. So that's why we use the infrared camera, because the infrared camera or radiometer measures just the temperature right at the surface. So we use infrared to measure the skin temperature, and we use a thermometer to measure the bulk. Now I wanted to show you a little bit more about this cool skin layer and how it has very interesting properties. So I'm going to show you a video of a demonstration that I did in my laboratory here, where I have a water tank that I'm going to fill with warm water so it'll be cooling off to the air. And then I have some pumps in the bottom of this. These are bilge pumps, like are probably on the sailboat for pumping out the bilge. We use that to shoot a jet of water from the bottom to the surface. I'm going to use a fan to cool the temperature down, and I'm going to use a rod to mix the water. And then I have a thermal infrared camera here that's going to show us what it looks like in the temperature map on the surface. So this now is a movie that I made in the laboratory of using an infrared camera, and you can see these beautiful patterns of temperature here. The range of temperature is about 3 degrees. Dark is cold, light is warm. And because there's a temperature difference between the water and the air, the water molecules right at the surface cool down a little bit and start to sink. That's where those dark lines are. Those are the cooling water sinking, and the warmer water is where it comes back up to the surface. Now I'm going to blow a fan on here, and you can see that when I blow the fan on there, it cools that surface down. But then when I stop blowing, the patterns come back. Now I'm going to shoot a jet from the bottom to break up that skin layer so you can see the really warm water from below. And there's the jet shooting up from the bottom, and you see again, it brings that warm water up and creates new patterns on the surface because of the warm water. Now, if I blow the fan on that again, it'll just cool it right back down. So you see that skin temperature is a dynamic process depending on if it's being mixed up, if it's being blown on by the wind. And now I'm going to pull a rod through, and I'll show you how you can mix it up if you're a boat. So a boat going through the water will mix up the temperature at the surface and bring up that water from below. But one thing I haven't been able to do is break that skin layer with my wind. I can blow the wind on it, it cools it back down, but you see I didn't bring up the really warm water from below. So to break that skin layer, you have to really blow hard, and that's what I'm doing now with my mouth. And you can see if I blow hard enough, then that skin layer gets destroyed by the wind, and you see the warm water from below. So that gives you an idea of what we can see in the laboratory when we use an infrared camera to look at the water. What does it look like out in the open ocean? So let's go to the next slide and see that. These are some of the first measurements I made in the ocean using an infrared camera, and I made them from a very special platform called Flip. And I wanted to tell you about this because I remember when I was in grade school, we had a weekly newsletter called The Weekly Reader. And they had just built this very interesting platform, which is very long. It's longer than a football field. It gets towed out to sea, and then they flood the bottom of it, and it flips up, and you have just this part sticking out where you can live and work and make measurements. So we put an infrared camera on the boom here, and we had these wires in the water that were measuring waves. And when we did that, we saw these very interesting thermal patterns coming off of the waves, coming off the wires. And those were the wakes due to the wires mixing up the water and bringing up that that warm water from below, breaking up that cool skin layer. And then they drifted away with the currents. So I want to show you what these look like under different wind speed conditions. This is a black and white image of this same image over here on the left, but it's zoomed out here so you can see those patterns, and then there's some reflection of the boom here and then a temperature front coming in. So this is what it looks like at 2 meters per second out on the ocean, open ocean. That's about 4 miles per hour in wind speed. Now, if we go to a higher wind speed, about 7 meters per second, that's about 15 miles per hour. You can barely see those wakes here. They went away. That's because the wind blew over the skin layer and thinned it out, so we don't see very much difference. But now if we look at data when the wind speed was really low, below 1 meter per second, then you see these beautiful convective patterns on the ocean that we were able to see in the laboratory. Okay, so now that we're all experts on the what the skin layer looks like, I'm going to ask the crew of the sailboat to tell me what they think made this pattern that we saw out in the open ocean, where a thermal wake was created by something on the surface of the ocean. And I'll give you 2 hints. One is that it was made in the tropical. These were measurements were made in the tropical Pacific, and it was made by a kind of fish. And also, when you go to the tropical Pacific soon on your sailboat, you'll probably see a lot of these. So can you guess what it is?
Saying it's a dolphin.
That's a good guess, but it's something it's a kind of fish that is on top of the water.
I'm going to say flying fish.
Yeah, it's gotta be
Yay, very good.
Yeah,
That is a flying fish.
We found plenty of them on our deck today.
Yeah, and a flying fish doesn't really fly. It uses its tail to put itself out of the water, and then it uses its wings to stay out of the water. So you see a lot of interesting things when you look at the ocean surface with a thermal camera. Okay, now let's get back to why we're making these measurements. You may have heard of the greenhouse effect. That's the effect that happens on the Earth, where the sun heats up the Earth, and then the Earth re-radiates that heat out into space. And because we have different kinds of molecules in our atmosphere, some of that heat gets trapped. One of the most important molecules that traps the heat is carbon dioxide. Now, the greenhouse effect is a very important effect, and it's a good effect for the Earth, because if we didn't have it, we would not be able to live, because we would lose all our heat to the atmosphere. But if we have too much carbon dioxide and other gases in the atmosphere, then it heats up too much. And that's what's been happening over the last several decades. And so it's very important for us to keep track of where how much carbon is in the atmosphere, so that we can understand how much the Earth might heat up and how to maybe cool it down. So we talk about the carbon balance. There are sources and sinks of carbon. Sources of carbon are human activity, and so that's where we put carbon into the atmosphere. A sink is like the drain in your sink where you put something down, and so we call the places that absorb carbon on the Earth sinks, and the ocean is the biggest sink of carbon. It's very important. It absorbs a lot of carbon and keeps it the balance that we need. There are other sinks like trees and the Earth, but the temperature of the ocean turns out to be important in terms of that carbon sink. And the reason for that is that cold water absorbs more gas than hot water. So if we have this cool skin layer right at the surface of the ocean, then it's going to absorb a little bit more gas than it would have than the temperature below would have if the cool skin wasn't there. So we can model that effect, and that's been done by some scientists recently, where they created this map of the global ocean where they're modeling how much more carbon dioxide gets absorbed by the ocean because we have this little cool skin layer on top of it. And the positive values here means it's absorbing more CO2 than it would if it weren't there. And if you add this up over the whole ocean, it turns out to give a 5% increase in the carbon dioxide sink. And that's a lot when you consider the global effects. And so this cool skin effect is important not only for heat transfer, but also for gas transfer. So we wanted to make measurements of this on the sailboat in its trip around the world, or around the Americas. So we've put a couple of different things on the mast and the hull. So here I have an infrared thermometer. It's like an infrared camera, but it only measures temperature at a point. And then I have a weather station that we put up there. And I don't know if you can still see me can you still see me in the camera?
Yeah, we still have you on the side.
Okay, so what I'm showing you now, this is an example in my office of this infrared thermometer. And you see it's not very big. It has a lens here that the radiation comes in, and then I can take the case off here. It has very sophisticated electronics here. It has an infrared detector inside and a little mirror here that rotates around, and it looks at a target inside and it looks at the target outside, and from that it can compute the temperature. And then our weather station is also very small and compact, but it's very powerful. It has an ultrasonic wind sensor in it, so it measures the wind without any moving parts. And then it has an air temperature, and then down below a relative humidity temperature to tell us how humid the air is, and then also a pressure sensor. So those are mounted up here on top of the mast, and that gives us the skin temperature measurement and our weather. And then we wanted to make a measurement of the temperature, the bulk temperature below the skin layer. And to do that, they cut a hole in the ship and put a temperature sensor in there, and it's about a 1 foot below the water line, which is shown here. And then we have electronics box that we put in here that records all that data. And then, quite remarkably, we have the internet from the satellite that we're using right now. And so I can monitor this is the output now of the weather station, and I can monitor the weather station, which I'm doing right now live from my office, and I can see that it's very warm air there. It's 83 degrees. Here's the water temperature. It's almost 30 degrees Celsius. They've got a nice wind speed here, and I can see that they're moving because I can see their speed is about 5 or 6 knots or nautical miles per hour. So this makes it so I can look at the data every day and see what's going on out there. And so it's really quite remarkable to have this kind of technology. So let's look at some of the measurements that have been made over the course of the expedition so far. So now you're familiar with the map of North America, and this is the track that the ship has been taking up through the straits between Alaska and Russia and all through the Northwest Passage. And what I'm doing here is I've color-coded the track to show you what the temperature is. So the colors go from 0, which is freezing, for blue, and up to 30 degrees which is about 85 degrees Fahrenheit. And you can see that most of the time it was not very warm, especially going up into the north here. They even got down to 0 temperature. But then when they came out around Canada from Halifax down to Puerto Rico here, the water temperature got much warmer. And now we can look at also the wind speed in the same way. I'm using the same color bar, but now it's in wind speed is in meters per second here. And you can see the winds got up maybe to about 15 meters per second. That's about 30 miles an hour up here on this part of the trip. But then when they came back around here, after leaving Halifax, you see this very bright red here. That's when the winds got up to 30 meters per second. That's almost 60 miles an hour. That's like how fast your car goes on the highway. So they hit a very strong storm here. And I want to show you a little more detail of the measurements through that storm. So I'm going to blow this up here. And this is the time when they were in the storm for several days. You can see the wind speed leaving Halifax was relatively low. And then right here, it gets up to about 30 meters per second before they got to Bermuda. And now we can plot next to that the color trace that shows the sea surface temperature. You see it warmed up from about 15 degrees centigrade to almost 30 degrees centigrade during the storm. Now, the air temperature also changed, but it didn't change very much. It went from about 10 degrees here to about 15 degrees. So during this storm, there was a very large temperature difference between the water, which was very warm, and the air, which is 10 or 15 degrees colder. So that creates a lot of net upward heat flux just due to the air-water temperature difference. And then the humidity, which is, again, that evaporation that occurs of the water, the humidity was very, very, we measure this in terms of what we call the humidity difference. Up here around Halifax, it was just down here around 0 to 4. And right here during the storm, it got to be very large. So we had very high air-water temperature differences, very large humidity differences that created unique conditions that I've actually never made measurements in before. Okay, so now what do these bulk skin temperature data look like during that storm or during the cruise? Well, first of all, I'm going to plot this now. This is my bulk skin temperature difference on this axis, and this is the wind speed going from 0 to 30 meters per second. And right here on this dashed line, I'm showing what we call a model. This is what we expect the data to look like based on measurements that have been made in the past. It'd be about half a degree here, and then it gets smaller as the wind speeds get higher. So what do our data look like when we plot it on here? Well, it looks like a big cloud of points. Maybe doesn't look like much right now, but I'm going to walk you through it here. And I've colored these dots here in gray by how much heat the ocean is losing. So the light colored here are in this cluster of dots here, and then very high heat fluxes out here when we get very high wind speeds. Now, because this data is so scattered and noisy, we have to average it in order to see what the trends really look like. So these traces now are where I take my data that's here, all this raw data, and I average it in 1/2 meter per second bins as a function of wind speed. And then I've also done 2 different averages. I've separated the data into 2 groups because you see there's kind of a group of data here and a group of data here that seem to be behaving differently. So for the low heat fluxes, I've averaged these points together here that are light gray, and you can see that this curve here, which is the data we measured, is pretty close to this blue line here. But then when we get to these very high heat fluxes at high wind speeds, it looks very different. And but it looks like it is making sense because it has this increase with wind speed. Now, no one has ever made these measurements of the bulk skin temperature difference above a wind speed about 15 meters per second or at these very high heat fluxes. So this is a unique set of data that I've never seen anything like that. And it's very exciting because no one's ever made measurements out at this wind speed, and we never would have seen that data before if they hadn't gone through that big storm. So one of the question is, well, why is it so different out here than it is down here? The wind is lower here, the heat flux is lower here, the wind is higher here, and the heat flux is higher here. Well, one clue might be if we look at pictures of what the ocean surface looks like under different wind speeds. 5 meters per second winds, you see some waves, but you don't see a lot of foam. The foam is generated by breaking waves that are caused when the wind gets higher. So at a higher wind speed, about 15 meters per second, you start to see these waves breaking. You see some foam here. But if you go up to 25 meters per second, that's close to where the wind speed that they were measuring during the storm. The surface looks very different. It's covered with lots of foam. It's very dynamic. All kinds of spray is blowing around. And we found by doing laboratory experiments that foam increases the heat flux or the transfer of heat much more than when you don't have the foam. So one of the likely reasons that we're seeing so much more heat being lost by the surface is because, and then causes the cooling that we see, is because of the presence of all this foam that gets generated by the breaking waves that occur at very high wind speeds. So to conclude, the sailboat One Ocean is a unique platform for measuring sea surface temperature, and the fact that they're sailing from the Arctic down to across the equator to Antarctica and back north provides a very, very wide range of conditions that are very interesting for us. And operating during the storm provided some unique skin temperature measurements at higher winds than have ever been measured before. So I'm sorry that they had to go through that storm because I think it was very scary. I've been on a research vessel that is several hundred feet long at wind speeds of 60 meters per second, and it can be very scary, and I would never want to be on a sailboat like that. So I appreciate all the efforts they made to get these measurements, and I'm looking forward to continuing to look at the interesting data coming from the sailboat. So that's all I have for my presentation, and I'd be happy to answer any questions.
All right, perfect, Andy. Thanks so much for sharing. I'm going to bring our crew back in here as well for some Q&A action. It was cool to see the pictures of Flip. I was on an expedition on the Nautilus a few years ago, and we were in San Diego, and I got a tour of Flip. It was a really cool ship to see, set up for when it's kind of horizontal, and then like the toilet and other things on the side walls for when it flips to vertical.
Everything has to rotate except
cool.
the toilets. They couldn't figure out how to do that.
Yeah.
So like I said, when I was in grade school, I remember that article, and then 30 years later, I was able to go on it as a scientist. So you never know where you'll end up and where your interest will take you.
All right, very cool. Okay, well, let's get some Q&A action going. If you're tuning in via YouTube, don't be shy. Use the chat sidebar. Any questions about what Andy just talked about is fair game. Of course, questions for the crew and how the sailing on the ship is going. I also see we have a little group, Garth Webb backstage, so don't be shy. If you want to send a couple questions in the private chat, we'll make sure we work some of those questions in. But the first question I have, Andy, is since it's really hard to measure that thin skin, how was it discovered in the first place?
Well, it really was some oceanographers before there were infrared sensors did try to make very careful measurements at the surface with tiny sensors. And you can do that in the laboratory because you can kind of control what the surface looks like, but it's very difficult to do that out in the open ocean. So it wasn't until the 1960s, when infrared sensors were developed to the point where they could make these measurements on the ocean, on the water surface. So people expected that this would occur, just understanding about how heat flux works from water, but they weren't really able to confirm that until they had the technology to make the infrared measurements.
Okay. The next question I have here is more related to climate change. So is our change in climate warming the skin up, and how might we see any impacts of that?
Well, in general, you can maybe think about first that the Earth itself is warming, and so the water on the ocean itself is warming up. So if the whole ocean water warms up, then that cool skin also warms up a little bit, but it's just a little bit cooler than the water below it that has warmed up. So yes, the cool skin is affected by the global warming as well.
All right. Question here. Michael, if you're not on board right now, who's doing the engineering? Who's making sure the engine's running?
Well, the whole crew that you're looking at there, throughout the whole expedition, we all took turns doing stuff engineering wise, and being a educator, I was trying to also bring them up to speed, right, on what to look for and how to interface with the batteries and all the other fun stuff. And so far, crew, thumbs up. I haven't gotten too many calls. I am available on the phone, but they're doing great. We refit the boat to make this 27,000 miles, and One Ocean has been performing very well. So.
All right, perfect. And Grace, with the change in plans, does that change when you will catch up with the crew again?
Yes, it will. Originally, I was going to fly down to the Falklands for the kelp sites, but now with the change of plans, it's kind of up in the air if we'll reach those southern kelp sites. But hopefully, I know the crew wants to turn left when they leave the Panama Canal. So hopefully, I'll be meeting up with the boat pretty soon. Might even fly down to Panama to join them there. So.
Okay. All right, Andy. Well, maybe I'll ask this question to a few people. This is from our group hanging out backstage. What got you interested in the research that you do, Andy?
Well, ever since I was a kid, I was interested in water. I grew up in Michigan, where there are the Great Lakes. And then my grandmother lived on Long Island, and we would go out to visit her in Montauk in the summers. And so I learned about salt water and the ocean there. And so as a young kid, I was always interested in the ocean. And that was when Jacques Cousteau was doing his research. And so I always wanted to be an oceanographer, and ended up doing that. Well, you do research, and you go and you get a PhD, and you do your thesis research in something. I was interested in waves. I did my research in that, but I used radar to measure waves. But then when I got to become a researcher, I tried to get some funding to use radar to measure waves, and the program manager said, "I've got too many people using radars. Why don't you look at this infrared stuff?" And I didn't know anything about infrared at the point. And I thought, well, I don't know, it's just temperature, right? But then when I got my first infrared camera and took it out on flip like that, I was hooked with all the fascinating things you can see and learn by understanding the temperature differences at the open ocean surface. There's a whole other type of research that we do using this, and that is to understand the mixing that's going on at the surface so we can model that. And by looking at the changes in the temperature patterns, you can understand how turbulent the water surface is. So one thing kind of led to another, and now I'm here making measurements for the sailboat.
All right. And let's flip that question to those folks enjoying a nice sail right now. What inspired you to be out on this journey, doing this research? It's a long journey. You've already gone through a hurricane. Why are you doing this?
You go.
Okay. I'm doing this. I'm studying environmental science, and I've always been really passionate about the ocean, and I love sailing as well. But being a part of a team that's collecting data and finding important information about the climate and sharing it with people and students is a really important thing to do, especially right now. So that's what inspires me to get going, is sharing all this information, and I love the ocean. So yeah, it's been really fun.
Yeah, I would say for myself too, I love the fact that there's such a big outreach going on with this program that we're doing. I love that we're collecting this data, but I really felt it was time for me to go do something to help the ocean as much as I can, because I love the ocean so much. I love all the creatures that are in the ocean. I love spending as much time as possible. So I decided it's time for me to do what I can to take care of this beautiful ocean. And honestly love reaching out to all of you students and teaching you about the ocean.
And I grew up in Nebraska, knew nothing about an ocean until I was 16, hadn't even seen one, but got fascinated through some other long passages. And I can see that we're all just connected. Everything that happens in the ocean affects all of us, and everything that happens on land affects the ocean. And I thought, why didn't I understand that in elementary school? Why didn't I see some of these issues and problems and study it then? And I just want people to know more about the ocean. We love it. That's why we're here. But truly, it needs some care. It needs some love.
I was on mute. Grace, I know that kelp is an area of passion for you. So why kelp? Why is that such an important research?
Personally, I fell in love with kelp, snorkeling and growing up snorkeling here in the Pacific Northwest. It gave me a chance to see how it's such a brilliant ecosystem full of so many different things, and that really caught my interest. And so after that, I've really enjoyed studying kelp and really figuring out what's impacting it and how it's doing in our oceans, if it's decreasing, if it's increasing, and because it's just such an important ecosystem for our oceans. So I really enjoy studying kelp in that sense and being able to see all the little species and critters that are in it.
All right. So, Michael, we should pose the same thing to you, way more on the engineering side of things, the ocean. What's led you to this?
Well, like Andy, I grew up in Michigan, fascinated by the giant lakes and everything. And then out west, the ocean, similar to when Mark, went out west and saw the ocean. So that's always been a passion. And what I bring on the engineering side, what I really got involved in with this wasn't a big ship gobbling up tons of, burning lots of fossil fuels. It was a sailboat, right? And from the last expedition, we have increased efficiencies. We have new batteries powering the science and all the stuff that Andy's recording, which are like 20% more efficient. And so everywhere along the way, we have changed and used less. And I feel like there's just a good message in how we can all do something like that. You can take whatever you're passionate about and apply it to what's going on around you. And so it's been super exciting. I've learned a lot, lifelong learner, just from everything we've done so far. So.
All right. Andy, I've got a great question that came in here from backstage. What do you think are our biggest gaps in oceanographic data? What would you like to see us gather more information on?
Oh, that's a good question. So I think the best way to think about that is to think about the difference between the measurements that we can make on land and the measurements that we can make on the ocean when it comes to, for instance, weather prediction. All over the world, the United States, there are hundreds of weather stations on land because you can put up a weather station pretty easily and record that data, and then you can use that to put into a model to understand the weather and to predict it. The ocean, we can't easily go out and put something in the ocean and get measurements from it. You can put a few buoys out there, you can have a few ships out there, but we have sparse data over the ocean for weather and climate compared to what we can do on land. Now, there's another revolution in oceanography that's probably on the same order as the satellite revolution that occurred in the last century, and that is the advent of drones and uncrewed surface vehicles that are like buoys, except they don't sit in one place. They can go out, and they can go out for months and make measurements in different areas and send that data back during satellites. So over the next few decades, we're going to see hundreds of these drones out on the surface of the ocean. Right now, we have drones underneath the ocean that we don't really see. They're called Argo floats. There's hundreds of them distributed around or thousands of them distributed around the ocean, and they're going up and down in the ocean, making measurements that oceanographers use to predict and model the ocean. And we're going to have that same type of technology on the surface as these drones proliferate and get cheaper and easier to operate.
All right, very cool. I'm going to share my screen one more time. Jennifer, remind me, what was the number of the buoy that just went in? Was it 151?
I think it's 157.
157? Okay, let me share my screen quick. It looks like if that was 157, it is already sharing some data maybe.
Ooh.
This one's set on 157.
What size height of waves? Because we have a little wager going on here.
Wave height over time. What's it measured on the side? Is that meters on the side?
Yeah, that would be meters.
Okay, so it looks like it's peaking. The highest one it hit was just over 3 meters.
Just over?
She won.
I think I won the wager.
All right, fair enough. So any classroom can go here. There's 2 buoys look like are active right now, 157 and 172. And you can check out wave height. You can check out position, salinity. Yeah, very cool.
That's fabulous if you're seeing 172 measurements. I haven't checked in the last couple of days. We had some glitches with that one to start with, but
Yeah.
I'm happy to hear if it's recording now. That's fabulous.
Yeah, it looks like measurements have come in. We'll assume it's still active here if it's showing up.
Oh, wonderful. Excellent.
Cool. Well, I think it's that time where we have to give a shout out to the classrooms for tuning in today. Thank you so much for those great questions. Andy, it was a real pleasure to have you join us and talk about the work you're doing and see some of the tools that you're using. Mike and Grace, great to see you. Not on the ship, but it sounds like you'll be catching up soon at some stage. And then I think we just need to see this view one more time. A little bit of blue.
A little bit of blue.
A little bit of ocean.
As we're talking, we see some of those flying fish around, and they're obviously helping, right, with the ocean.
Yeah, perfect. Well, we will have more dates to announce soon, classroom, so keep your eyes out for that as we continue to follow the progress. For now, though, I hope everyone has a great rest of the week. Smooth sailing for our team out on the ocean, and we'll connect again soon.
Thank you very much, Joe. Thank you, everybody.
Thanks, everyone.
Thanks,
All right. Thanks, everyone.